I'm very happy to be here to talk about my journey to a flying quadcopter built from scratch. I tend to speak a bit fast, so please, if it's the case, just stop me with a big move. So I hope you will enjoy. First, who am I? I'm Loic. I'm 28 years old. I studied computer science at the University of Louvain-la-Neuve, that's in Belgium. And since then, I'm mainly active in software administration and software development. You can follow me on Twitter, drop me an email, or Facebook me if you want. I'm a co-founder of Spin42. We are 3 guys that help teams to build more scalable and better products using Lean and Agile. We work on all the aspects of an IT project, from system infrastructure to the user experience. Well, let's start with my story. So I think everybody has been overrun by work at some point and needed to relax. And personally, I like to play sport, and the nerd side of me playing with new gadgets. So I started to search on the web for the latest trendy new gadget, like a smartwatch, a VR headset, IoT, and everything else. And then I saw this everywhere on the web. That's the biggest drone race took place in Dubai. So several things have drawn my attention. So the first one is that the price for the first place is $250,000. And then the winner was a boy of 15 years old. So yeah, that was enough to convince me that that would be my game. So I started to check where I could buy this kind of racing drone. So you have 2 choices. Either you can build ready to fly without anything to do, or you can buy each part separately and make the assembly by yourself. And that's what I did. So I spent some time to select which kind of motor or frame and all the pieces that I wanted for my first drone. Then I put everything together and configure it. Yeah, that was my first drone, so I didn't know what to expect. And so my first fly was a big fail, and I broke this one after 1 week. And so after build and rebuild, I found that very impressive the way they were flying. That's super smooth, stable, and fast. And so I wanted to know more. I wanted to know how a quadcopter works. And for me, the best way to understand something is to try it by myself. So I started to read some article about the operation of a quadcopter, and then the idea of creating my own quadcopter from zero started to obsess me. Yeah, that's cool, but I didn't want it to build something just for myself. So I saw that there are more and more people involved in makers and do-it-yourself stuff. And so I wanted to build things that attract those group of people because they do amazing stuff. And as a developer, I know that contributing to a project takes a lot of time. So I wanted to make the project as easy and fun to contribute. And finally, I decided to build my own quadcopter from scratch, and I identified 2 key values that needed to be part of the project's mindset. First, it should be understandable. So my thought is that taking leverage of new technology in software development is very important. So those kind of projects are usually research-oriented, so they're not the easiest to understand and contribute. And for me, they lack a bit of structure and usually use low-level language like C. That's awesome, but difficult to manage and not very attractive for the newcomers. So I wanted to break those standards by shipping a source code that not actually work, but also well organized and use high-level languages that are more friendly for the most of us. The next is that it should be extendable. So after seeing a lot of amazing things on websites like Thingiverse, I wanted to give people the desire to contribute and unleash their creativity. So using tools like a 3D printer is those kind of contribution and gives the possibility of fast and cheap prototyping and provide a lot of different materials. Additionally, we are now trying to make stuff smaller and de facto impossible to upgrade. So my focus was also to use building blocks that are more easy to connect together, and they should be easy to add or upgrade. And finally, I didn't want it to use expensive dedicated hardware like a dedicated flight controller, but instead taking leverage of a board like a Raspberry Pi, BeagleBone that are cheap and more powerful every year. Well, here is a big picture of this presentation. So I will first dig into the design choice I made. Next, I will explain all the components of the quadcopter by making an analogy to the code when it's pertinent. Then I will talk about the first flight of the quadcopter and how I've debugged it. And finally, we'll spend some time to talk about the future of the project. So let's start with the design choices. As compute unit, I choose a Raspberry Pi 3 because it's easy to find, it's powerful, and it's a foldable platform. And they are constantly improving their design and performances. Plus, it has a lot of connectors like classical input-output interface, I2C, SPI bus to communicate with the multiple sensors and actuators. And finally, it comes with a built-in Bluetooth and Wi-Fi. Well, obviously, I choose Elixir, but Nerf too. So with distributions like basic Linux for Raspberry Pi, you need to configure the network, then install SSH, then connect to your device, then check out your sources of the project, and then maybe finally run it if there are no missing dependencies. So that's a lot of steps that you always have to repeat. And so for me, default distributions are not well suited to embedded systems that need to boot fast and without boilerplate. So with Nerve, you can put your application you are actually working on from your computer to your Raspberry Pi within 30 seconds. So you just need to create a firmware, which is actually an image of your application, and then using a simple command, then burn the firmware on the SD cards, then insert it into your Raspberry Pi, then power up your Pi, and it will boot up within 10 seconds. That's very fast to boot and easy to update the code. You just need to focus on the code and not on the boilerplate anymore. Well, let's talk about the building blocks of the quadcopter. So I will show you how the application is organized along with explanation of the main concept that allow the quadcopter to actually fly. So the idea behind this talk is to give you the ability to understand the basic of a quadcopter, and so that maybe you can build your own after. Well, basically, a quadcopter is a big loop that repeats indefinitely until you turn it off. So first, it gets information from sensors, then it performs some computations with the sensor values, and finally, send a signal based on the computation to actuator, which are the motors in this case. So the graph here is an overview of the building blocks and the order in which they are actually executed in the code. Here, just a small subset to have an overview of the brain supervisor tree. Sorry. So the brain is the name of the main application under the umbrella. There are actually 3 apps, about which we'll talk later. So the brain, the drivers, and the API. And basically, every component is a separate process on the Raspberry Pi. I use a gen server for each to allow leverage of multiple CPU cores. Well, thanks to the Elixir supervisors, when a process crashes, it is automatically restarted without crashing the whole application. I also use multiple supervisors that group gen servers into subsets like sensor or actuators that can have different restart strategies. There is a code sample. So the sensor that you want to use are declared into the configuration as well as the driver that the sensor needs to use. So on top, you have the code snippet that is used to declare the sensor in the configuration, and that's a simple array that tells which are the sensor, and then by sensor, you have the driver associated. Then on the bottom, the code snippets of the supervisor that fetches all the sensors from the configuration, then spawn and supervise them. So now I will explain all the components one by one in more detail. So let's start with the sensor. So the main and basic goal of those components are to get the tilt of the quadcopter. So by tilt, I mean the angle on every axis. And for this, we use 2 sensors that are the accelerometer and the gyroscope. So each one has advantage and disadvantage, and we'll see which they are. So the first sensor is the gyroscope. It measures the angular speed of the device on 3 axes. So the angular speed is the speed in degrees per second at which the device is moving around an axis. For example, if the device is not moving, it will output 0 on every axis. If you keep moving the device along an axis, it will output the current speed and output 0 if you stop. And to get the device tilt from the angular speed, we need to compute some integral of the angular speed over time. On the graph, you see that the values are drifting with time. I don't move the device, and all the angles are still changing fast. And that's the main issue with this kind of sensor. Next, we have the accelerometer, which is a device that measures the acceleration of the quadcopter on 3 axes. For example, if you lay the device flat on a table, it should show an acceleration of around 1g on a single axis, which corresponds to the gravity of the Earth, roughly. And to get the device tilt from the acceleration, we use some trigonometry with the portion of acceleration applied to the axis. On the graph, you see the illustration of the sensibility to vibration. So the device was on a table, and I was constantly hitting the table with my hand, and peaks up to 20 degrees were reached, even if the device was laying flat. Well, in practice, a sensor is composed of code from 2 applications under the umbrella that splits on top the business logic from the bottom, which is the interaction with the hardware. So on the brain side, the top, the code defines how to interpret the data and when to fetch the data. On the driver side, so the bottom, the code defines how to get the data from the hardware, what are the instructions that need to be sent to the device for the initialization, or to read the registries that contain values. In the driver, we also have the bus, that is through which medium the instructions are sent to the devices, like I2C or SPI. So I use Elixir ELE that does a very great job to handle those kind of communications. As I said, we need to get the precise tilts of the quadcopter. So we have to use a simple formula to get the best of the 2 sensors. So this formula is called the complementary filter. It takes a big ratio of the gyroscope and a small one of the accelerometers, and this allows to compensate the accelerometer noise and the gyroscope drift. On the graph, you see that are the same setup done before, and now the angle are, for the 2 axes, more stable. The next component is the receiver. The receiver is the component that will receive all the commands sent by the user and its transmitter. So each button, switch, or stick on the transmitter is called a channel. So the receiver component will have to handle all the data sent by the hardware. It sends indefinitely all the channel value as fast as it can to the receiver in a package that we call a frame. The frame is a sequence of bytes that start with a sync byte. It's a well-known value, and then it's followed by all the channel value encoded in 2 bytes. So we need to parse this frame to get the numeric value of each channel. In practice, there's basically the same logic than the sensor for the split of the concern. So the single difference here is that it communicates to the hardware device through UARTs. So I use the Nerve UART library to handle this kind of communication. The next component is the interpreter. The interpreter takes the receiver channel as inputs that are valued between 1,000 and 2,000. And from the point of view of the quadcopter, those values doesn't mean anything. So we need to convert those values to meaningful ones and that is the role of the interpreter. But for this, we need to know a bit more about 2 flight modes. So the first one is the rate mode. So for example, we tell the quadcopter to turn at a specific speed, let's say 30 degrees per second, and then the quadcopter will continue to turn at this speed. The second one is the angle mode. So we tell the quadcopter to tilt to a specific angle, let's say 40 degrees, and the quadcopter will turn and then stick to 40 degrees. So the goal of the interpreter is to convert the channel values to meaningful value for the quadcopter. For example, if the tilt of the quadcopter is maximum 45 degrees, and we push the transmitter stick to the right, let's say a value of 2,000, the interpreter will convert this channel value to an angle of 45 degrees. And we call the result of this conversion set points. That's the value that we want to reach. So set points are very important for the next parts that are the PID controllers. Well, PID controller is a control loop feedback mechanism. So the basic idea behind the PID controller is the following. It takes sensor value and set point as input, then it computes the best output for the motors until the set point is reached. Let's see a PID in action. So that's an example for the quadcopter tilt. So a PID continuously computes the error value as the difference between the set points and the procedure variable, which is the tilt in this case. Then it applies a correction based on the 3 coefficients called proportional, integral, and derivative, which are tuned to get the optimal response, the throttle in this case. So let's go with an example. So the flow is the following. First, you define a set point to be reached. Then the PID controller computes the response with three coefficients, the set points and the process variable. The response is applied to the quadcopter, and then the tilt should be affected. But there are other external factors like the wind that can also affect the tilt. And finally, the sensors measure the actual tilt and send it back to the PID controller, and it starts again until the set point is reached. Then we have the mixer. The mixer distributes the right amount of throttle to the right motors. So if the quadcopter needs to go ahead of 10% of stability and left of 25%, the mixer needs to figure out which motor have to change of speed. So the mixer has to deal with the three main movements of a quadcopter that are the roll, the pitch, and the yaw. So the roll is the move around the y-axis. So to play with this kind of move, you have to increase or decrease the throttle on the motor on the left or on the right. Then we have the pitch. The pitch is the move around the x-axis. So same idea, but for this we have to change the throttle of the front motor or the back motor. And the last is the move around the z-axis. That's called the yaw. Finally, to play with this kind of move, you have to decrease the throttle on the motor on the same diagonal. And finally, the mixer takes all the movements and combines them to output the amount of throttle applied to each motor. That's the basic idea of all the components of a quadcopter. Well, I made the software development at the same time as the printing of the pieces. So in this part, I will show you all are the different steps of building the pieces of the quadcopter and try to make it fly. So on the left, we have the prototyping of the connection. So on the right, the same box where I stacked the Raspberry Pi with a plate to allow to secure the IMU, which is the inertial movement unit, which are the board with all the sensor and other sensor if needed. And I put the PWM generator on the back to use the connection with the motors. That's the final box with all the connections. So I printed the box using transparent PLA to allow seeing the LED of the Raspberry Pi. I left some space for the HDMI port and the power supply. Well, I was quite new to the 3D printing world, so I learned a lot by making a lot of mistakes. On the left, you have the main plate, which takes around 20 hours of printing, and I filled this one around 3 times. On the right, you have the assembly of the base plate and 2 arms. So 3D printing is awesome, but it can still be very complex when you need to make precise pieces. I will not go into 3D printing and electronics in this talk, but if you want to, we can discuss about it later. Well, at the end, the result is pretty cool. Almost everything fit perfectly together. The receiver, the Raspberry Pi sensor, ESC, and motors. So the time for the first flight was come. Well, if you're wondering why there are some books, it's because I put a cord between the books and the quadcopter to avoid it flying in my face. But obviously, that's a fail. So at this point, I knew that the most of the work was to come, so I needed to know what was going on the quadcopter to be able to debug properly. But using some serial or HDMI cable on a flying machine is not the easiest thing to do. So I needed to find another way to get feedback from the quadcopter, and so I developed a component called Black Box and another application called the ground station. So almost each component is used as input of another, so I thought it was a good idea to track the final result of each component separately. So I created this component called Black Box that exposes an interface to allow all the quadcopter components to log their outputs. So the communication between the quadcopter and the ground station is achieved by phonics sockets for real time. For example, each sensor will send to the black box the values that are read from the hardware, or the mixer in this case will send the computed throttle repartition for all the motors to the black box. And all those data allow to make easily some plotting and interpretation on the ground station. Here are two samples of code. So one represents the code that sends the data from a component, in this case a sensor. On the other side, we have the black box that parse and store the last events. So I made difference between events and loops. An event is like a sensor read, a PID results, receiver channel value. And the loop groups all the events that are linked each other. Remember the graph, the first graph about the building blocks. And to summarize, at the first point, the component calls the trace function with its module, process name, and data. And at the second point, the black box processes the event asynchronously before storing it into the loops buffer. And then the black box sends the last loop to the ground station through the socket periodically. That's the ground station. It consumes the events pushed by the quadcopter and plot them on multiple graphs. So the ground station is an Angular 2 application, sorry. And on this dashboard, you can see multiple things. So first, you have the graph of the raw value outputted by the accelerometers and the gyroscope. And on the bottom, you have the output of the complementary filter explained before. There are other graphs not shown on this picture, like the loop time, which is the duration of the main loop, meaning the time in milliseconds required to do a complete loop, and the repartition of the throttle on the for motor, and so on. I also needed to be able to adjust parameters on the quadcopter based on the black box feedbacks. So to achieve this, I exposed an API to a Phonics app, which is actually the API app under the umbrella that allows to change the configuration for some components of the quadcopter. So it looked like this. So I already implemented the PID tuning for the API, from the API. You can choose all the coefficients for all the PID controllers started on the quadcopter. During the developments, I frequently moved the quadcopter between my home and workplace, and so the IP address assigned to the quadcopter was changing frequently. So I needed to find a way to avoid swapping the IP address in the code each time I changed of location. So I searched on the web to how I can solve this issue, and I found the Nerve SSDP library. So SSDP stands for the Simple Service Discovery Protocol. It does not use neither DHCP or DNS. Basically, the host or ground station request on the whole network using multicast for all the available services. Then all the available services on the network reply to this request directly with the IP address, the name, and some extra information is needed, if needed. And thanks to this library, I don't need anymore to bother about which IP address is assigned to the quadcopter to communicate with it. I just request it when it's needed, and that's all. For example, on the quadcopter side, we start an SSDP server that listens for all the requests. That's the first point. And on the second point, on the host side, we ask on all the network for the services, select those named helicopter, and then extract the IP address. When I was training the quadcopter, I usually didn't put it in front of me, but as far as I can in the room to avoid injury. But I was a bit boring because each time I found the bug, I need to bring it back to my desk, swap the SD card with a new firmware. So it took me a lot of time to make small changes during my tests. Then I used the Nerve firmware HTTP library to allow updating my firmware for the network without swapping the SD card. So I created a mixed task that leveraged SSDP and HTTP firmware update. So it first searches for the quadcopter, then build the firmware, and then push it through HTTP to the quadcopter. And thanks to the library, it's automatically updated and restarted. And that saved me a lot of time. As you see that a few lines of code, and we have first step to discover a quadcopter, then to build, and then upload to the quadcopter. Well, testing a quadcopter can be very dangerous for me and my teammate. So to avoid an accident, I bought a trampoline net that I fixed on the roof with some magnets. And thanks to this, I escaped a lot of injuries during my test. Then after some tuning and update of the code, it looked like this.
Time keeps on slipping, slipping, slipping into the future. Time keeps on slipping, slipping, slipping into the future. I wanna fly like an eagle.
saw it fly, and that's cool. It was a kind of a big victory for me. So it still flickers a bit, but way better than before, and it's a good step forward. So during this try, I only used the proportional gain on PID controller because the other are more tricky to tune due to the soft real time of the Erlang virtual machine. Then actually, I lie a bit. So the video that you previously shown are the one of the first version of the quadcopter. And since then, I put a lot of effort to improve the design for a smaller and easier to carry and safer version of the quadcopter. So actually, this version is deprecated in profit of this one. So it's smaller, so I can easily scratch it on my bag. There are some protection on the propellers that are flexible to resist small crashes. I put sensor on some side-on block to minimize the vibration. Then if you are more confident, you can easily remove all the propellers protection to gain some weight. So I'll bring it with me there. So you want to see during the break, just come and see me. We can have some discussion about this. So let's talk about the next steps of the project. So for me, there are two big points. First is to improve what is actually there. So I started to mock component like you are at I2C to make some tests, but test coverage is still very low, and I need to add some more tests. Then the PID controller use only proportional gain coefficient, so I need to spend some time to tune derivative and integrative correctly, but those are difficult due to the soft real time of the VM. Then make Bluetooth works on Raspberry Pi with Nerf to have a remote shell on the quad. I see a guy that started yesterday to implement this, and that's super cool. He has to continue this. That's fine. And there are sensors already on the board that are still unused. We can use the magnetometer to hold the orientation of the drone, use the barometer to hold the altitude. Then we can find better way to leverage some Erlang VM tricks to reduce the loop time, and add driver, sensor, receiver, and so on. The second point is to innovate. So that's a cool platform to play with. So we can imagine all the capabilities of expansion. That the simple one could be just adding a GPS to define a roadmap, then implement some video recognition to follow people. There are a lot of libraries for that. And I made some 3D design to allow stacking multiple Raspberry Pi on the quadcopter if needed. Then we can add some sonar to avoid obstacle, implement Kalman filter instead of complementary filter. There are a lot more possibilities to play with. Then I'm very happy to open source this project. So all the parts are on Thingiverse and the code are on GitHub. So we should really check Nerf and the library around it because it's going to be amazing. And I don't think I will win the Dubai drone race yet, but at least I understood how quadcopter work. And that's all for me. It will be all around if you want to see the drone, and don't hesitate to find me if you want more precision. Thanks.
So we have a bit of time for questions if anyone wants to ask one. Sounds good.
Sorry?
So
Not yet. I'm too heavy.
I'll just work my way over as we go.
Hello.
Hey.
Hi. First of all, congratulations for the work. It's pretty impressive. Have you think to explore ways of doing something like real-time firmware upgrade?
Not yet.
Not yet.
Because I have to find a way to continue some information to the motors when the Raspberry Pi is rebooting. So we need to add some more hardware that save the last command send and then maybe reboot it. But kind of tricky. But that's a good idea.
That's an idea. Okay, thank you.
Cool. I think there's a couple over here, so if you raise your hand up, I'll come find you.
Have you by any chance also heard about the Crazy Fly? And
Sorry?
About the Crazy Fly, it's a drone that's flying autonomously. I'm not sure.
I don't understand.
I guess there's a company called BitCraze.
Yeah.
They have an autonomous flying drone.
Yeah.
Using, like, they put sensors in a room and then the drone can fly automatically. So maybe it's interesting. But you haven't heard about it?
No,
Oh.
no. I will talk after.
I thought you're from France, right?
Yeah.
Yeah, these guys as well. So I thought maybe, like, if you...
Cool.
Cool project, by the way. Really cool.
Let's talk after.
Thanks. So who else over here had a question?
did you have issues with the battery, with the Raspberry Pi? Doesn't it consume too much battery?
Sorry, the battery?
Doesn't the Raspberry Pi consume too much battery?
No, no. Actually, the Raspberry Pi is like less consumer battery. Like to have an idea, the 4 motor can consume I think 100 amps. So Raspberry Pi is like 500 milliamps. So that's okay.
Great. Who else had a question? You had one too? I'll come back over here next. How much juice did you get on the Raspberry Pi? What was the longest?
Sorry?
What was the longest amount of running time you got on the Raspberry Pi and the battery?
I think maybe 5 minutes.
I have two questions. One for the determination of orientation of the quadcopter. You use the accelerometer's acceleration sensor.
Mhm.
How do you compensate for the acceleration of the quadcopter? Because when it is hovering, you have just the gravitation, and when you accelerate, how do you know which part of it is your acceleration and which part is the gravity?
In fact, it's always relative acceleration. So, and as I said, the formula with the complementary filter is like taking 99% of the gyroscope and only 1 of the accelerometer. The accelerometer is just there to avoid the gyroscope to drift. So the measure of the gyroscope, the accelerometer are almost not taken into account.
One more question, is the 3D printing, the drawings for the 3D printing available?
There are on Thingiverse. So if you go on the GitHub repo, you will see a link to the Thingiverse design.
Okay, great. Congratulations on the design.
Thanks.
Did anyone else have a question as well?
Hi.
Hi.
My question is, so have you ever tried to fly as far as possible, and if so, what's the maximum distance and altitude you've ever reached?
No, because due to the regulation now in Belgium, it's a bit tricky to do kind of stuff. And it's kind of full tolerance, but if it's not, I've lost all my work. So I will wait a bit to be sure that when the signal of the transmitter is lost, it will just fall. I think it's okay, but I have to try this kind of stuff. And the goal is not to fly far away, but just to have some kind of a developer kit to build upon a quadcopter and to enjoy about it.
Does anyone else have another question?
Hi, how much would the hardware cost?
Not so much. I think the Raspberry Pi is like 40 euros. The PWM is like 20, and the sensor like 40. Then you have the motors, but you can choose whatever you want. There are plenty on website that cost a lot. But yeah, I think that's the motor, the more expensive. But you have to deal with are they effective or not. So that's you to choose. But I think with 100, maximum 200 euros, you have the wall.
Okay, thank you.
Thanks.
Super. Anyone else? We have a bit more time, so if you, as long as you're willing to keep taking the questions.
Thanks.
Hiya. So you talked about the discovery of the drone over the SSDP, or so that's is that a HTTP or TCP connection?
No, that's different. SSDP is really low level. It's like it uses UDP and multicast. So that's behind. That's not HTTP.
Okay.
That's before, but it's pretty simple. I think it's what your TV used to broadcast there in the room. So it's used in small network. Yeah.
Did you consider, once they've discovered, actually creating a single Erlang cluster with the controller? Is that what happens now, or do you send commands over some other mechanism?
Now, actually, I left some space for the code to handle multiple quadcopter. But actually, I just take the list and take the first. But maybe you can just select the one you want. So each quadcopter can have a name and so an IP address assigned. And then all will respond with their IP address and their name, and that's up to you to choose which one with the name you want to select and to send the data.
Okay, and then once you've selected it, you join them with Erlang?
Yeah,
or you
I just store the IP address of the one selected and then communicate with it like this.
Yeah, how do you communicate with it?
With a Phoenix socket for the quadcopter from the ground station, and then through a REST API with Phoenix 2 from the ground station to the quadcopter.
Cheers.
Super.
Yeah, thanks. So just a quick question. Have you considered selling everything as a kit? I mean,
actually, if some of you guys are interested, you can just send me an email. Maybe I can check with some 3D apps to make some kits of 3D printed pieces and make some kind of bill of materials with all that stuff. I can do this, but if someone is interested, I'll make it.
Okay, thanks.
Thanks. You should continue to develop your Bluetooth stuff.
I will do. But can you elaborate a little bit about the soft real-time features versus hard real-time, what you usually would use when you do something in the traditional way?
Actually, I'm not a big guy in a VM of Erlang, but I have some issue with kind of garbage collection that happen whenever, and then because all the PID computation are based on time, except of the proportional gain, I need to find a way to measure the time, but in a really reliable way. That's some kind of difficulty. So I see that there is some priority on the process. I have to see what are the best, how to tune it to avoid my process to be swapping off for other useless process. But that's some way that I need to investigate. It's a bit more tricky, so we'll spend some time on this. Thanks.
Does anyone else have another question? If you have the stamina to take another one. So, going once. Oh, there we go.
You used two umbrella apps. Were they under one big one or just separate umbrella apps, and then you built releases for the individual ones?
Sorry, the what?
You had two umbrella apps? The brain one?
Three instead, yeah.
Three?
We have the brain, which is mainly all the business logic like the PID, receiver, and so on. I have the API, which is only a Phoenix app to interact with the brain. And then I struck the drivers because there are a lot of different hardware that you need to implement some command to initialize them. And I didn't want it to put it in my business logic. So the third umbrella apps is like not an app, but it's the drivers that contain all the code for the hardware.
Okay.
So I shown that you can select, for example, which are the sensors that are active, like the gyroscope, and then after you can say, okay, my gyroscope used the driver L3, this driver, which is for this hardware. Yeah.
Okay. Thanks.
Super. Well, we should probably wrap there just to make sure there's enough time for people to transition. But did anyone else have another pressing question, or should we wrap it up there?
Just see me after if you have more questions.
Yeah.
I'll see you there.
Awesome. Well, thanks. That was a super presentation. So.
Thanks.